CO9, complex geometry facades. When we start thinking about freeform facades, complex geometries, it's always the question of how do we close the surface and how do we get the substructure done. This is an say simple version of a freeform complex facade, the grid shell systems. What we see is this is the main structure, this steel bars here. Due to the very slender structure, this whole thing needs to be pre-stressed with a cable mesh. The cable mesh is what we see here. This is where the cable mesh appears. And then on top of it, glass plates, insulated glass units in this situation, which are actually straight and then have an iterating surface to create this freeform shell. Rather simple one with only in both radians are oriented in the same direction, so it's an synclastic curvature, which has then at the edge obviously the difficulty to get qua geometry the connection to the foundation, to the base, to whatever kind of component you'd like to add it on in position. Quite interesting shapes of glass plates. We're going to see more complex ones later in this lecture. It's nicely designed here by wrapping it with an inner and outer layer so that you don't really see the connection, how it is done. Next one, anticlastic curvature, so same orientation of radiance in here, and then contradiction of the radiance at this area, same cable grid system, so the main bars with the pre-stressed glass, and then the outer surface, as you can see, this is the typical shell with a synclastic curvature, and this is the edges with an anticlastic curvature. I like this project a lot. It's in Berlin. I like it a lot because they're very, very nicely managed to deal with the edges and with the glass plates all being straight, not buckled, not bended as glass plates, but creating this entire geometry very nicely and very, very sharp as a system. When we continue with this one, another project in Berlin, which is a double shell structure with the synclastic and the anticlastic area, and then this shell, which would be entirely a structure, is cut off for aesthetical reason for the entrance situation in here. Cut off means that the shell itself is cut. Penetrating a shell means you need to deal with additional forces in these situations. That's what they saw with a huge profile. You rarely see it here at the edge. A huge profile which takes down all the components of the grid shell structure and then takes the load and then transfers the load to the foundation, to the base. That can be done in steel. Can be done in steel as a system, but we also can envision that this at the edges creates an interesting shape of glass plates, and this is an IGU unit with a super small triangular IGU package. This is my shoe, shows the dimension and makes clear where the complexity in geometry appears when you'd like to deal with this. So this is installation phase. We see the cable grid system, the bars and the pre-stress, the connection of the cables, and then the glass plate and the cover plate, which fixes the glass in position, and the guy is installing it as a system. When we try to get rid of regular freeform structures to really freeform structures, this is a sample done in Delft, which shows a more rather experimental setup. Okay, there's a certain aesthetically driven geometry which is developed, and we see that the complexity then appears. How do you close it? How do you wrap this as a system? How do you get the connection of the main steel system to the facade system? It's rather experimental in this setup, but the same architect managed to do a lot more advanced project in Utrecht, an outer house where you see there's an main structure and a freeform shell structure, which has an additional layer of glass support structure, so glass frame system, which is add on top of this shell structure. So there's a main structure, and then there's a glass system, a frame system, actually kind of stick system, which is on top of this system, which then keeps the glass in position as a setup. How it is done here. And now this one, where we see super advanced polycarbonate glass plates. So the glass plates are not straight anymore. It's they're they were expected to be free-form curved. This was at that time not possible in that quality in glass, so they ended up in polycarbonate plates, and you see the polycarbonate plate being free-formed. Polycarbonate is simpler to form. Obviously, you need to deal with fire, which is a certain aspect, so the outside of this structure needs to be sprinklered. These nozzles are made to prevent snow falling down if there's a snow situation, that it sticks to the system. But we also can envision it needs a super complex substructure to create this outer surface in this, say, nice curved area. Which brings us to the next one, Franco Gehry and the developments they did. It starts with this Bilbao Museum, where we see it's a huge free-form structures. The strategy he chose to create this nice smoothly surfaces instead of having flush glass plates or pre-curved polycarbonate plates. He ends up in zinc shingles. So shingles on top of each other, which then by the size of the shingle allow to follow the line smoothly, the line of the geometry which is expected. Again, the question is how do we create the substructure, and this is the sketch of how the substructure is done. We see as an outer system the outer shingles. We see a subsystem for the shingles to fix, 1 or 2 layers of the subsystem, and then we see the main structural system, which creates the structure as itself, and then takes the loads from the subsystem and the shingles as in geometry. So this, when you look at the big picture, this is the main structure, and then the secondary structure brought in position to create the smooth surface, and then shingle as a covering system. This is deeper evaluated and developed for this Walt Disney Convention Concert Hall in Los Angeles as another Gehry project, and we see how nicely they managed to get these free-form surfaces done in shingles. They even are able to get the rain gutters integrated in these systems so that they don't appear. And when we will see the system behind, it's again the same setup. We see the main structure, which is this one, main structure, which is this one. Then we see a first layer of a secondary structure, a second layer of a secondary structure, a third layer of secondary structure to create a smooth surface, and then that whole thing is covered with the shingles, which we see here at the inside of this system. A next one, this is tiles laminated on a substructure. Again made out of a steel main structure, then a substructure, and then the tiles are laminated to this system. Interesting design, very nice design, also qua say aesthetic and color, very impressive. But laminated laminated tiles on a structure, that's something which you need to say investigate and prove that this technically works for a certain time. This is what we can see at the inside. This is main structure. Main structure is then followed with an inner and an outer layer, doing all the functionalities for the building envelope, and then roof the tiles laminated on top of it, and then there's an opening for a window, which we see is done with the spider system, rather simple principle system. When we look at these kind of free-form geometries, when we start thinking about the systematic which we always follow in facades, outer layer has to be rain-tight, inner layer has to be watertight, and in between this function zone takes the loads and the insulation. We can imagine that, say, this complex facades are not that simple to create when we have to develop a free-form skeleton structure which then needs to be wrapped. This Elbphilharmonie project in Hamburg, they wanted to have this outer surface. They needed to make the rain-tight layer for the roof with, say, a limited number of penetrations. So getting each of these spheres being fixed to this rain-tight layer would deliver a lot of penetration, with the consequence that they built this entire substructure to carry these loads and fix these substructure at some very limited positions to make sure that there's a limited number of penetration of the foil below, which is, say, the one way of creating this outer surface, which is the one aspect. And when we go inside the building, we see it's a super free-form geometry, which then, functional zone, needs to get insulated in this area, and then air tightness at the inside needs to be entirely sealed at the inside to make sure that there's no humidity getting into the system. And you can imagine that all this aluminium foil being brought in position, that's quite an intensive craftsman work to get done, and leakages appear where the craftsman doesn't work perfect, or where you're not able to get your fingers in to get the geometry in the end done. That can be an say very intensive work. What we identify is we want these free-form geometries to be made. We are still at the situation that we only able to make skeleton-like structures, and then these skeleton-like structures are suffering the problems to be watertight at the outside, airtight at the inside, and getting the insulation in between. So it's still an systematically possible, but not nicely and smoothly developed technology. Interesting experience. And with this, I go to where this all comes from and do stop again.